So limit is a really important idea to calculus. So we're going to introduce some concepts about that. Um, Here's the definition of a limit. I would say this isn't strictly the most technical mathematical definition of a limit, but it gets us the basic idea. So if f of x, so when we say f of x, we're talking about the output of a function, becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is L. Sounds really technical, but it's actually not too technical here. Let me draw a little bit of a picture. So we're talking about graphs. We're going to be looking at a lot of graphs as we see what limits are. So let me just sketch some random curve. So this is a nice continuous curve. Looks like it might be a cubic, whatever. Let's say we wanted to know what the limit of this function as it approached 2. So what we're talking about is on the x-axis as the graph approaches 2. Well, we can easily see right there is our point on our graph that's at 2, right? You can go up there and see it. And the other thing that this mentions in the definition is that it approaches from both sides. So we're talking about as we approach 2 from the left side and as we approach 2 on the right side. We can see that our graph is converging. That's the word I'm going to use. It's going to the same place on both sides. That's going to be an important thing for limits, is we want to make sure that our graph is converging from both sides on a single point. Well, whatever this value is, that is a horrible color. I don't know why I chose that. It's not a horrible color. It's very hard to see. So it's converging on that point from both sides. And whatever this number is, this would be considered our limit. Whatever the y coordinate is there, that would be what we would call the limit of our function as x approaches 2. Would be this particular number, again, whatever it happens to be. I mean, on this graph, I have no idea. It could be, depending on the scaling, it could be anything, right? This could be 10 or 100 or 50 or 2 or whatever. It just depends on the scaling, but I'm just going to call it L for limit. So the limits are going to be the y values as we approach a certain x value on our graph. Now, not all of them are going to be this easy. Sometimes our graphs are going to be doing weird stuff. Sometimes they might have holes or asymptotes or all kinds of stuff going on, but this is a kind of a fairly basic limit and looking at what happens to it and how we kind of think about what a limit is and talk about what we mean when we say as x approaches a certain value. So what we're talking about here is as x approaches 2 from both sides, from the left side and from the right side, are both included there. Hopefully that gives you a brief introduction to what we're talking about with limits, and we can kind of look at a bunch of examples and see more specifically different ways that we can identify what a limit might be. Okay, so let's look at this example. Right up here is kind of the notation that we're going to be using. So that's not very good. Let me use the box. There we go. So this is kind of the notation that we're going to be using. This says the limit as x approaches 2, so as it approaches 2 from the left and from the right, of this particular function right here. So this is our function that we're looking at. It's a simple linear function. We have a graph of it. We actually have a table of it here, and we're going to kind of make sense of identifying it. So as we approach 2, right, we're getting closer and closer to 2 from the left side and from the right side at 2. Our graph is also approaching a particular point. From the right side, it's approaching this 4, and from the left side, it's also approaching 4. From both sides, our graph is converging on this singular point. So we say that the limit of this function as x approaches 2 is 4. It's very simple. We can see it graphically what's happening, and it's happening from both sides. As we follow it from the left, it's going to 4, and we follow it from the right, it's also going to 4. That's an important thing. Not all of our graphs are going to be doing the same thing on the left and right side, so we have to be careful with that. We want to make sure that on both sides, it's converging on that particular number. Now, the other thing we can do besides looking at the graph is very useful, and we'll do that a lot, is we can also look at a table. So what I have here is an x, y, or an input-output table for this function. And you can see I'm getting closer and closer to 2. I just typed in some numbers that were getting closer and closer to 2. So 1.9 is pretty close to 2. 1.99 is even closer. 1.999 is even closer. And you can see how these numbers right here, the outputs, they're converging on what we know the limit to be. These numbers, as we get closer and closer to 2, are also getting closer and closer to our limit, which is 4. And that's happening on the left side, right? 1.9 would be on the left side of this. And we're just getting closer and closer from the left. And then here, we're getting closer and closer from the right. So we have 2.1, 2.01, 2.001. We're getting closer and closer to 2. And we can see how these numbers are getting closer and closer to 4, which we know is our limit. So obviously, our limit ends up being 4. For a function like this, it's actually not really necessary to go through all this craziness that we're doing here about getting closer and closer to 2 and checking it from both sides because this is a straight line. This graph is about as boring as it gets, right? There's no curves, no nothing. It's just a straight line. We know that it's approaching the same number. We can even find the specific point, no problem whatsoever. So later on, when we talk about how to actually figure out limits without a graph, this is about one of the easiest problems we could get. We would literally just plug 2 in, do our calculations, and figure out the answer. But that's not what we can always do. We're going to see some examples where it's a little bit trickier, a little bit harder to decide what maybe is going on. But if I just plugged in 2 here, if I just did 3 times 2 minus 3 times 2 minus 2, that's 6 minus 2, 4. We get the same thing right there. We get the limit. This one we can just evaluate. We can just plug the number in that we're going to, figure out where the graph's at there, and we're good to go. So this is like kind of our really easy limit. Again, they're not all going to be this simple. We want to start with something easy. Let me clear this. Okay, example 2. Now, obviously, we have a much weirder function going on here. We're looking at this thing, and we're looking the limit as x approaches 0. So again, remember, we want to make sure we're checking as x approaches from the left and from the right. So from the left side, and from the right side, it seems to be converging on this point, right? Seems pretty obvious that this answer is going to be 2. However, there's a bit of an issue. If I plug in 0 into this function, it's actually undefined. If I put a 0 here, let me just do this real quick. If I put a 0 in there, 0 plus 1 plus 1. This becomes 1. The square root of 1 is 1. So we get 1 over 1 minus 1, which is 1 over 0. We're not allowed to do that. We're not allowed to divide by 0. So when I actually plug in the number that we're looking at, there's an issue. It's undefined there. We can't divide by 0. So what I'm actually learning by this is I'm learning that this graph has what's called a hole. Just at this single point right here at 2, there's a hole, meaning right there at that number, it's a problem. I could put something just a little bigger than 0 or a little bit smaller than 0, That'd be fine. Wouldn't be a problem. I can do that. And you can see here that I was able to do that, right? I was able to put something just a bit smaller than 0, even negative 0.001. So really close to 0, but not quite 0. You can see how this number right here is super close to 2, which we see as our limit. So I was able to put something just a tiny bit smaller than 0 in there and get a number. And I was able to put something just a tiny bit bigger than 0 and get something that's also really close to 2. So our graph, as we get closer and closer to 0, is approaching 2. And we still consider this to be the limit. This is the actual limit there. Even though the graph is undefined at 0, the graph does have a limit at 0 as x approaches 0, because our outputs are approaching a set value, which looks like 2. I mean, looking at these two, the number that would be in between those is 2, right? So this one's a little more complicated, but still something we can do there. All right, let me clear that. So this is something else that can happen if we're looking at a graph with a hole. It could be undefined at that particular number. So we couldn't just plug it in and figure out what the limit is. We actually had to look at the values around it or look at the graph to see how we could find that limit. And then another example here of something else that can happen is this. So this is a weird equation. We got absolute value of x over x. You can see the graph of it here. And again, we're looking as x approaches 0. So we're looking at as it approaches 0 from both sides. Well, if we follow the left side of the graph is approaching -1. But if we follow it from the right side, it's approaching +1. So what is it? What's the answer? As x approaches 0, is it +1 or is it -1 or what?
Plus or minus 1.
Good question. Could be good guess. We could maybe say it's plus or minus 1, or we could maybe split the difference and say, I don't know, between that, I guess it's 0. Actually, neither of these are the answer, unfortunately. And because the function is also undefined at 0, because if we put a 0 there, that's a problem, what we actually say in this case is we say that our limit does not exist. Because this graph, when we look at both sides, it's not approaching the same number. It's not converging on a particular output. Actually, it's weird. It's actually constant. I mean, it's approaching -1 on this side, and it's approaching 1 on this side. So in the middle, what's going on here? I don't know, nothing. We say that the limit does not exist. We'll go over some other cases where the limit does not exist, but this is one of the cases where a limit does not exist, if it approaches different numbers on both sides. Another thing here that I'll get into, we can talk about the limit on the left side and the limit on the right side independently. So we could say that the limit of x, absolute value of x over x, as x approaches 0 on the negative side, that does exist because we're only looking at it on the negative side. So from the left, that it is -1. Or we could talk about it only from the right and say that on the positive side, it's +1. We can look at the individual left side and right side limits and talk about those values if we want to. But overall, the limit as x approaches 0 from both sides at the same time doesn't exist. All right. There are three cases where a limit does not exist. So these are illustrations of these cases down below. So the first one is f of x approaches a different number on the right side than from the left side. So that's what we just looked at right here. On the left side, it approached -1. On the right side, it approached 1. Therefore, no limit, or the limit doesn't exist. The second option is if it increases or decreases without bound, meaning it just goes up to infinity or down to infinity. We also say that the limit does not exist, so that's right here. If we think about as it approaches 2, if we go from the left side, it's going down to negative infinity over here, right? It's going down forever. And on the right side, it's going up forever to positive infinity. Technically, these are also different numbers, so we could almost use the same reason as number 1. But if it's ever approaching an infinite number, or the words they're using without bound, keeps going up and up and up forever, down and down and down forever, then we say the limit does not exist. So anytime we have vertical asymptotes, that's going to happen. Vertical asymptotes, our graph kind of runs into them and goes straight up or straight down. So, and then weird messes like this. When the graph oscillates, so goes up and down between two fixed values. So in this case, it's hard to see, but this is +1 and this is -1, and our graph is just bouncing up and down super fast. And so at 0, what's happening? I mean, there's like a bajillion points here right around 0, anywhere between 1 and -1. So we just say this limit does not exist either. This function is sine of 1 over x, if you were interested in it, but this one also does not exist. Yeah, there's no way to figure out what's going on. Even if we zoom in infinitely close, we can't really see what's going on there. It doesn't really approach anything. It's like all of these values between -1 and 1, just kind of bouncing back and forth. So that's the third one. This one's much more rare. These other two are very common, where we have a different right and left side or vertical asymptotes. So these two, very common. Third one, not so common, but important to know. Okay, I'm gonna clear this. I didn't clear that. There we go. Okay, so I briefly talked about this. We can talk about the right-hand limit and the left-hand limit. So the left hand is from the negative side, so we just put a little negative after the number. That way we don't confuse it and think it's -c. We just know that it's from the negative side what the limit is. So in that case, if you have a graph, you're only talking about what's happening from the negative side. So if you're approaching a particular value, C, you're only approaching it from the left side. You don't care about what's happening from the right side in this case. Or in this case, when you're coming from the positive side, the right side, you only care about it coming from that side. But if these are different, then we say the limit does not exist. So it's important to know we can talk about the left-hand limit and the right-hand limit, but if they're different, we say the limit doesn't exist, so oh well. It will be useful in our explanations. You know, if we're talking about the reasons why a limit might not exist, we can specifically say, well, this limit doesn't exist because the left-hand limit is 5 and the right-hand limit is 2. Therefore, since they're different, the overall limit does not exist. So talking about these individually is important to explain why or why not a limit would exist or not. All right, clear those. All right, so here is that second graph that we're talking about, and I'm just kind of illustrating it a little bit more. Again, anytime our graphs have vertical asymptotes, which can happen when we have rational functions like this, a function with x in the denominator, we can always create these vertical asymptotes. And whenever we have vertical asymptotes, generally we say the function does not exist. Now, I hesitate to say this, but some people say this differently. Some people do say that that a limit like this might exist. Not this one in particular, because they go different directions. But if you imagine this graph on this side also approaching infinity and this not being here, since they both approach infinity, some people might say that this limit is infinity. That's just something some people say. Doesn't really matter, make much of a difference. For our class, we're going to say it does not exist. If a limit is infinity, then it doesn't exist. That's all we're going to say in here. But some people, you might run up, you know, you take calculus in college or whatever, or next year. I don't know the way that Mr. Bushline talks about it, but I just want to say that people talk about these differently. Some people think limits can be infinity, and some people say that if the limit is infinity, then there is no limit. It's just a small distinction. Yeah, but in this case, no one would say this limit exists because it's different. Even if you're using infinity with your limits, you would still not say that this limit exists, because on one side it's negative infinity, on the other side it's positive infinity, so they're different values anyway. So this one does not exist, D and E. All right. Hopefully I confused everyone sufficiently. So there are some properties to limits. They're relatively intuitive. So if the limit of some function is L, if you raise that function to a power of n, then you can just raise the limit to the power of n, and you'll get the right limit. Or if you take the nth root of that function, then you can just take the nth root of the limit. The reason we might do this is just because it would be obnoxious to raise something to a certain power. We can just kind of think about the much simpler function and find that limit, and then just raise the limit to the power rather than the whole function to the power. So it just kind of saves us some algebra work of raising a function to a power and evaluating that more complicated thing. Same with the radicals. Honestly, we probably won't make too much use of these, but they do exist, and it does help us prove certain theorems when you get into calculus. So there's that. Here's an example. So we have a real simple function, x plus 4. The limit as x approaches 5, well, we're allowed to just put a 5 in here. There's no problem caused by that. So 5 plus 4 is 9. That's how we got that limit. Well, if we square it, if we square that original function, then our limit is just going to be squared. We're going to get 81. If we take the square root of that function, then we just will take the square root of our limit, and so it'll be 3. I mean, I could plug it in also if I wanted to. I could do a 5 here or a 5 here and figure this out. 5 plus 4 is 9, 9 squared, 81. 5 plus 4 is 9, square root of 9, 3. We could do it that way too, and maybe that's just as easy. But if we happen to know a limit already, you can just kind of work with it there with these small changes to the function. Pretty easy. Yeah, pretty easy. So what I'm doing here, where I'm putting that number in, this is going to be kind of the first method that we have other than graphing to evaluate a limit. And it's going to be kind of the first one we try pretty much all the time. We're going to just try to substitute. If we can just plug the number in that we're looking for, good. That's what we want. So if we look at this first example right here, we're going to try to evaluate this limit by direct substitution. When I look at it, I want to see, okay, I don't see any problem. It seems like I should just be able to put 1 in here, right? I can put a 1 in there and square it and subtract. That seems fine. So 1 squared minus 1, that's 1 minus 1, that's 0. So it seems like this limit is 0. Now, I won't often use direct substitution alone. Usually I'll combine direct substitution with looking at the graph just to make sure it's converging from both sides on that particular value. But direct substitution generally is going to be my first approach when I'm trying to figure out a limit. Take your number and plug it in. It's that easy. So let's look at example 2. All right, example 2. I can plug in 2. Let's see what happens. Let's see what happens when we do that. 2 minus 2. 2 squared, 3 times 2 plus 2. Okay. Choking on something. 2 minus 2 is 0. 2 squared is 4. 3 times 2 is 6. 4 minus 6 is -2. -2 plus 2 is 0. Uh-oh. This is a bit of an issue. Really, 0 in the denominator, that's our main problem here. Whenever we have 0 in the denominator, we consider this to be undefined. So what this is telling me is that I can't do this by direct substitution. I'm going to have to actually take a look at the graph. So that's what I'm going to go ahead and do. I'm going to open up Desmos and take a look at this graph. Try to keep that in my head. Desmos. So x minus 2 over x squared minus 3x plus 2. Okay. Interesting. I'm going to clear my drawings. And so looking at this graph, there's definitely a vertical asymptote here, right? The vertical asymptote actually looks like it's at 1, not at 2. Remember, we're looking as x approaches 2. That's the limit we're looking for. So we're looking for it as x approaches 2. I can see what the problem is as x approaches 1, right? Because if we type in a line here at x equals 1 and we make it an asymptote, we can see that there's definitely a vertical asymptote here. But the question is, why is 2 okay, 2 is undefined. So our graph actually has a hole at 2. There's a word for this when our graph has a hole. It seems continuous, but there's a particular spot that causes a problem. This is called a removable discontinuity. It's a removable discontinuity because, well, it's a discontinuity because it's a hole. Our graph, our function is undefined there. When we try to plug in 2, we try to divide by 0, and that's just not allowed. The reason it's considered a removable discontinuity is because our graph is a smooth curve, except for this one tiny little issue. There is a hole there, but it appears that our graph converges on it from both directions on a particular value. It looks like our limit here is going to be 1, right? We can see it looks like this limit is 1. As we approach from the left side and approach from the right side, our graph actually does converge on a particular value. And we should be able to put in numbers that are just smaller than 1, just smaller than 2, and just bigger than 2, and get really, really close to 1. And the other reason that we consider it to be removable is I can actually change this function. I can factor this and simplify this. So if I factor the denominator here, x squared minus 3x plus 2, this actually factors as x minus 2 times x minus 1. And here is me removing the discontinuity. X minus 2 on the top and the bottom, go away. we were able to factor out that discontinuity. So this graph is the same exact graph as this. But there's a hole right there. But if I graph this function, it's going to give me the same graph as that one. I was just able to factor it and cancel out some terms that were causing that discontinuity. Now, these are fundamentally different functions because one of them has the discontinuity and one of them doesn't. But notice how they line up directly on top of each other. But this graph is not undefined there. This green one, the one that I factored out and canceled stuff, this one is actually defined at 2, whereas our other one, when we follow it, is undefined there. These are not the same function, but this one helps us figure out what the limit of that one was, because we were able to remove that discontinuity, the hole that our graph had, by factoring and canceling, and therefore we can see that it does actually approach 1. I kind of scrolled the graph. Oh my goodness. There we go. When I removed the discontinuity, I could actually see that the graph did approach very specifically the number 1. We're going to talk a lot more about functions and kind of evaluating these things, and in particular discontinuities and removable discontinuities and asymptotes and all kinds of things like that. Yeah, that'll be it for today. We got like a minute. Remember, make sure to have any homework questions that you've got ready for tomorrow, because it doesn't have to be for what we were doing this week. Could be from previous weeks, because we'll have some extra time tomorrow, and I'd like to help people out. So.